Hi, Dr. Pitcher here, and I'm going to start my presentation. And my sample presentation, I'll be talking about serine proteases in laundry detergents. These are a type of enzymes that help clean our clothes. All right. Now, as far as there we go. As far as what enzymes are, they're really nature's catalysts. They'll increase the rate of chemical reactions, and a lot of different types of reactions are catalyzed by enzymes. And we can see those in this slide here. There are 6 main categories, and the one that we're interested in is the hydrolysis. So that's number 3 here. And those catalyze hydrolysis reactions. And serine proteases are an example of hydrolysis. Now, what is hydrolysis? Well, hydrolysis is the breaking of bonds, covalent bonds, with the addition of water. So we can see here a peptide, and we're adding water, and we've got an enzyme to catalyze the reaction, and we end up getting now a carboxylate and an ammonium. And we can see here that the carbon-nitrogen bond is split. Oxygen of H2O ends up on that carbon, and the 2 hydrogens end up attached to the nitrogen. We have a net addition of water, and we're breaking a bond. All right. Now, these serine proteases, for example, there's one called subtlysin, are used in laundry detergents to help break down difficult protein-based stains, for example, blood. By hydrolyzing the protein stain into smaller peptides or amino acids, it may be easier for surfactants, detergents, to remove the stain. I'd like to talk about the serine protease mechanism, but before I do that, I want to provide a short introduction to curved arrow notation. You'll see this later on in organic chemistry. So we'll use a curved arrow, and 1 arrow equals 1 pair of electrons. Arrows always start at a lone pair or a bond, and end with the arrowhead at a nucleus or a bond. And they're used to depict the step-by-step breaking and formation of bonds in a reaction. And on the bottom here, we can see here's an alcohol, which is a Lewis base or a nucleophile, and that pair of electrons goes to form a new bond with that carbon and this acid chloride here. That carbon is a little bit electron deficient because the carbon-oxygen bond is polar, and it functions as a Lewis acid or electrophile. But we don't want 5 bonds on carbon, so we have to push 2 electrons up onto the oxygen, and we get this product here. So let's take a look at the serine protease mechanism in action. In the first step, we have nucleophilic attack by a serine, that's a type of amino acid, serine in the active site. So the side chain of serine has an oxygen, which will engage in nucleophilic attack. And this forms what we call the tetrahedral intermediate, which is down here. This carbon has 4 things bonded to it. So in the starting material here, that carbon is trigonal planar, but then in the tetrahedral intermediate, it is now tetrahedral. The next step is cleavage of this carbon-nitrogen bond to form what we call an acyl enzyme intermediate, where part of what was the enzyme, half of the enzyme is attached, half of the protein is attached to the enzyme, and then the other half is just sitting in the active site. That swaps out with the water. So this blue part of what was, half of our peptide pops out, and the water comes in, and now we can get third step, which is nucleophilic attack by water on the acyl enzyme intermediate to make a new tetrahedral intermediate. Now, these red arrows show the final step, I should say, and that is the loss of the other half of the cleaved protein, and so this part was from the old protein that we started with. And so we'll regenerate our serine, and so our enzyme's back to what it was. It's a catalyst. It's neither consumed or destroyed in the reaction. And now we've got the other half of our enzyme. And that can repeat over and over again. So in conclusion, these serine proteases are commercially important enzymes used in laundry detergent, among other things. This mechanism is very well understood. I was able to show it to you. And it's also a good example of catalysis of what would otherwise be an unfavorable reaction. And if you want to look at any of the references, here they are. I have a couple of textbooks, and the Wikipedia pages on subtolysine and enzymes in laundry detergents are actually pretty good. All right, well, thanks for watching, and feel free to leave comments.